Hello everybody. Today I'm going to show you how you can use a software package called SageMath to verify your math. So SageMath can plot functions, can solve equations, but it should be used to verify what you have done, not independently. So the way you install this software, really you have to sign up to the online version. You go to sagemath.org and select CoCalc. And that's a platform that runs SageMath. So I'll show you how to do this. And once you click on this, you will see a sign up button. You click on the sign up button, and then before you have to enter your details. Before you enter your details, you agree to the terms and select Python and SageMath. So let's do that together. So what I've done here is I've searched for SageMath. You can go on Google and search for SageMath, and the first choice or the option you get is SageMath generally, and then you scroll down and click on CoCalc, and then you do a sign up. So when you do sign up, you agree and make sure you click on SageMath and Python and enter your details below, and then you'll get to a screen of this nature. Then you can click on SageMath here, and above that you will see your projects. You can click on your projects. If you don't have any projects, you can start a new project and give it a name. This takes a little time. I'll pause the video and start again. And at this stage, you can say new project and give a name to the project. We can say Sage Plot, because that's what we are going to do today, plotting a Sage. And make sure you click on Sage Workbook, and then you'll get to this screen. So before we do any further, let's go and plot something. Learn how to plot something on paper, and then we'll come and verify it on SageMath. So for plotting, we'll do something very simple. We'll plot y equals x, just the graph y equals x. We'll divide the paper into two, and y equals x is a line, a function of a line, equation of a line, and we know that the equation of the line is y equals mx plus c, where m is the gradient and c is the intercept. C is where the line crosses the y-axis. So if you compare these two, we see the gradient is 1 and intercept is 0. So this line should cross the y-axis at 0. So we see the function has a positive gradient. That's a line with a positive gradient. So we say it is y equals x. So if we look at y equals minus x, has a negative gradient, no intercept, and that would be the exact reflection on the y-axis. If this is the x and this is the y, it would be a reflection on y-axis, where the gradient is negative, and we'll name this y equals minus x. Having known that, now we know how to plot a line with a positive gradient with a 0 intercept, positive gradient of 1 with a 0 intercept, and a positive gradient of negative gradient of minus 1 and a intercept. So next thing we'll do is we will plot y equals x plus 1 and y equals x minus 1. So these are the two. So we will look at this graph. So this is same as this, but it has an intercept of 1. So it crosses the y-axis, it's shifted up, crosses the y-axis at 1, 0, 1. X is 0, y is 1 here. So this is x and y. And here it's the same gradient as this, but it crosses the y-axis at -1. So it is 0, -1. And this is the line of this. So let's look at y equals -x minus +1. So it's this axis, we move it up so that we get an intercept at 1. So we have an intercept at 0, 1. And here the intercept is 0, -1. This is y equals -x minus 1. So you can take this, if you know the graph of one graph, you can move it up and down to represent the intercept. This is how, when the intercept varies, you draw a graph based on the gradient and intercept. Next thing we'll do is go to SageMath and verify what we have drawn. So in SageMath, it's very easy. What you say is plot x. We want to plot y equals x in the range of x between -5 and 5. So that's what you want it to plot. That's the simple command there. So if you run this, you'll see that it has plotted the graph that we drew as y equals x. So if we change this to -x and run to show that it's the exact reflection, I'll move this further up, reflection. Then if you say x plus 1, first we'll draw x, y equals x. And if we increase the c or the intercept and we'll run that, you see that it will jump up. It's moved up. I will move that up a little. It just moved up. And we can do the same thing with -1. And we say run. So it was moved down so that it has an intercept at this point. So the intercept is at this point at 0, 1. So we'll go back and draw more graphs and come back to Sage and verify it. So I will divide the page into 2 again, and let's see whether we could build on what we have learned. So we know y is equal to x is this graph, x and y. And if we take y equals 1 over x, if we take y equals 1 over x, it would be, see, when x is equal to 0, it's not defined. So it would be a graph of this nature. That is the y equals 1 over x. Then if we do y equals -1 over x, it will be a reflection on the y-axis. We saw that earlier, to be a reflection on the y-axis. So we have this and like this, x and y. Similarly, we'll plot y equals x squared. Y equals x squared means it's if when x is equal to -1 and 1, it's the same value, but because x is squared. So it is a graph and it has no intercept. So it is a graph of this nature, right? Now if we take y equals x squared plus 1, it has an intercept now. So it has to be moved up so that it will intercept at 1. This is 0, 1, right? And if it's y equals x squared minus 1, it will move down and the graph would be of this nature. It would be symmetric and it will cross at 0, minus 1, cross the y-axis, and this is x-axis. So now that we have drawn these, let's go back to Sage and verify our graphs. So here we had this graph x between x minus 5 to 5. What we do is we want to plot x squared. So if you run x squared, you will see our graph was correct. So that's the x squared. What about x squared plus 1? So it has an intercept of 1 now. Just a second. It has an intercept of 1 now. It has moved up. And if we do minus 1 and run, it will have an intercept of minus 1. So it will, there you go, it has an intercept of minus 1. That's when it crosses the y-axis. So if we do, again, we'll go back to basics. We'll show y equals x and then show 1 over x. Excuse me. We show 1 divided by x. So you see the asymptotes and you see that the plot at 0 is not defined. So it goes like this, just like we drew that. And if we say minus 1, to be the opposite. It's a reflection of the on this axis. So you can say, if you zoom in and say 0 to 5, instead of minus 5 to 5, it will zoom in and show you only this quadrant, but you see how it asymptotes the x-axis and y-axis. So next we will draw y to the power ex. So divide the page again. So y to the power ex would be graph of this nature, where it intercepts at 0, 1. Y equals ex. Then y to the power e minus x would be this, the opposite of this graph. Or not the opposite, I mean the reflection on the y-axis. Let's also draw y equals ln x. So ln x is a graph of this nature. Sorry, I didn't draw that right correctly. It doesn't cross the y-axis. Asymptotes at the y-axis, y0. So this crosses the x-axis at y0 at 1. This is y and x. Then minus x is y, because ln minus x would be this nature. So let's verify. Let's plot ln x, where x ranges from minus 5 to 5. There should be another parenthesis, because the parenthesis, left parentheses have to match the right parentheses. So that verifies our graph. So the next thing we will plot e to the power x. So we'll do e to the power x. Just a second. It's e to the power x. and we'll run that. That's correct. Sorry about that. That's the graph we plotted as well. So we can continue to work on that. So next we'll work on sine x and cos x. So we'll divide the page into two again for comparison. So on this side we'll draw y equals sine x. And on this side y equals cos x. So on sine x is when sine is 0, sine x is 0, sine is 0. So it's a graph of this nature, and it peaks at +1 at pi over 2. And here pi over 2 is 3.14 radians over 2, and this is pi. That's where it crosses. So as for cos x, it's shifted when cos x is 0, cos is 1. So this is cos x. It oscillates between -1 and 1. So this is cos x. Here again it's pi over 2. In radians it would be 3.14 divided by 2 and so forth. So if we draw y equals sine minus x, what will happen is you draw a reflection about the y-axis. So let me try to do that. It's of this nature. That's sine minus x. But cos x doesn't move. It's the same thing in terms of minus x because it is already symmetrical on the y-axis. So y equals cos minus x is the same as y equals cos x. So we'll verify this using SagePlot. So in SageMath we say plot. We were plotting e to the power x. We say sine x. Okay, and we count the number of parentheses to say whether the left parentheses are the same as the number of left parentheses are the same as the number of right parentheses. So looks like, and if we run that, we get sine x, and we can change the sign to minus sine x and run again, and you get the reflection. And we can change this to cos x, and run, and we can also change it to minus cos x and run this. And you see that this is 2 and 4 units because these are in radians. Okay, if it was degrees, it would be 90 and 180. The next thing we'll do is take a complicated function like this and plot it on SagePlot alone. So it would be, let me erase these, and we'll say plot. We need to plot x to the power 2 plus 1 over 2 times x to the power 2 plus 3 times x, and we will put another parenthesis here and have another parenthesis here, and we also say, and we say it is between x is between -2 and -0.1. Let's see. So when you run this, you get a graph of this nature. So we were able to plot this as well on SagePlot. So it is a plot command, and when there is a when it's 2x, you have to say 2 star x to the power 2. So in other words, this equation has to be written as, maybe I should write this. I'll compare this. It's like if you say plot x to the power 2 plus 1 over 2 multiplied by x to the power 2 plus 3 multiplied by x. This matches this matches this. Then we say x from -2 to -0.5 or any value, the range. So that there are, on the left side you have 1, 2, 3 brackets. On the right side you'll have 1, left have 1, 2, 3, 4. On the right side 1, 2, 3. Then we need another bracket on this side to complete that. Okay, hope this was helpful.